Get it? All right, I'll begin. Heavenly Father, we thank you for this day. We thank you for the break. Just pray that you'd be with us today. Help us to glorify you, Lord, and we do. And you know I pray, Lord Jesus. Amen. All right, so I figure what I'd do is just look at the notes here for a bit with you guys. And and then I'll go on. Let me make this bigger. So we've been talking about, integration with respect to 2 or 3 variables. And let's see here. So let's see here. This one is pretty mechanical, right? Integrate from -1 to 5, integrate from pi over 6 to pi over 2 of cosine y dx dy. So here's a question I would add to this. So if you had to tell me, so that's the integral of what function over what region, and what does it represent? Could you answer those questions? Again, that's the integral. What's the integrand? What's the domain over which we're integrating there? Right? And what does it represent? I'll get you started. The integrand is what? This is not a complicated question. The integrand is cosine y. That's the function we're integrating. What is the, this is an iterated integral we're looking at, right? But this is a setup of a certain geometric integral that we defined, right? This would be something like the integral. So again, I say this is the integral over some region of f dA, where f of xy, like you guys just told me, is cosine of y. How about r? R is equal to what? It's xy such that what? -1 less than or equal to x less than or equal to 5, and pi over 6 less than or equal to y less than or equal to pi over 2, right? That's the setup. We're integrating over a rectangle, right? What does this mean? What does this answer mean? 3. Geometrically, what is that? So here's that rectangle, right? And then over that, I'm not sure what it looks like exactly, but here's, z equals cosine of y, right? And the volume bounded between r and the graph of cosine y over that region is 3. Now my picture may be absolute garbage. It may be that cosine dips. I don't know, does cosine have a 0 in there? Oh, cosine of pi over 2, right? My picture's not quite right. Cosine of pi over 2. So if this is pi over 2, of course this graph is actually down here, isn't it? And so forth. But yeah. Actually, that graph, you could graph that actually somewhat successfully. We're going between pi over 2, pi over 6. This is pi over 6. Over here's pi over 2, let's say. So pi over 3 would be here, right? What's cosine of pi over 3? Cosine of pi over 3 is 1/2, right? Cosine of pi over 6 is root 3 over 2. Cosine of 0, of course, is 1. So I can't draw it quite right, but oh well. Anyway, it's something like this, right? That's the graph in the x equals 0 plane, and that thing just kind of, it looks like this. This is actually a picture. It's something like that. Kind of like a piece of corner doweling or something like that, just kind of rounded one side and then the right back like that. But anyway, the volume there, 3. Oh, I'm sorry. And I neglected. It went from minus, this is x equals to 5 right here, right? It went to x equal to where? -1, right? So my picture's not quite right yet. It goes actually back here past the y-axis a little bit, right? Does visualizing that shape that we're finding the volume of actually matter to calculating the volume? Yes and no. Like it matters. It depends on whether you're trying to calculate the volume or the signed volume. If you're trying to calculate the signed volume, it doesn't much matter if the actual graph dips below the xy axis and above, right? Because the volume and the signed volume are the same. But to be careful, to calculate the volume between the graph and the xy plane, you should probably integrate the absolute value of the function. Just like we did in Calculus 1, if you want to calculate area bounded, you have to be careful not to let the signed area below the x-axis cancel out unnecessarily. All right, I'm digressing. This one example is almost the same thing. Let me go on here. Here's a nice one. We have the solid under the plane 3x plus 2y plus z equal to 12. This is, I mean, did I almost give you guys this problem to work in the daily quiz? I think I might have, but this down here in the xy plane, I kind of visualize that being this r, and then I think about the triangle sort of projecting down to that triangle r in the xy plane, and so I want to integrate over r the function 12 minus 3x minus 2y, and that should give me the volume bounded. Now here, we have some variable bounds to sort through. So, oh, but I did it a little bit different, right? I found to find the volume, I integrated f over dA, right? The way we did it in class before the break was what? We looked at a triple integral, didn't we? So instead of this, we did the integral over, dz dx dy. But the inside integral was what? Integrating from 0 up to basically 12 minus 3x minus 2y. So actually, after you do the first integral and the triple integral that we looked at, you get to the same starting point as we got to here. This is the thing. We can look at triple integral. We can calculate volumes either as integrating dx dy dz over appropriate volume, or we can also calculate volumes by integrating a function over an area, right? If the volume we're looking at is actually bounded between the graph of a function and the xy plane, right? So the context matters, but... uh-oh. What? Hey. What? Oh, not cool. Not cool at all. See, well, anyway, these were supposed to have had errors found and fixed. I just found a rather significant error. This setup, what should we do? Can you turn the lights on for me? Let's think about this here. So this, if we just to set up the integral as a triple integral. So start with dz, then go to dy, then go to dx, right? So starting with try to think about sculpting this region. Start with, I would notice that x goes between 0 and 4, right? Then if you focus your attention here, that is y equals, this right here is, what is this? Y equals to 6 minus 3/2, right? At z equal to 0. But the point is, this y equals to 6 minus 3/2 x, that's the furthest the shape ever gets out from the origin, right? Like if you think about the vertical plane that has this line in it, if you just chop that off, so you start by chopping the space into this infinite slab between x equals 0 and x equals 4. Then we take that slab, we cut off, y negative, chop it off at the xz plane, all right? Then you take that and you chop like this along the y equals 6 minus 3x plane. That leaves you with a, if I can draw it, foolishly try to draw it, that would leave us with this. Right, and we should also chop at the z equals 0 plane, right? Or sculpt or whatever. What's the operative word for sculpting? To mold? Not really mold. I don't know. Sculpting. Sculpting is the verb. Okay. Words. Okay, so the what I'm trying to say is we're saying it's bounded by the coordinate planes, right? So we've got 0 less than or equal to y and 0 less than or equal to z. Those are given to us because we're told that the volume is it's bounded by the coordinate planes. So that puts 0 as our base, our bottom bound. But y, you see 0 less than or equal to y less than or equal to 6 minus 3 halves x is what should go there. See, because that would limit me to this shape here. Then to chop it further down to actually get that shape, I have to limit z, right? Because as my picture is currently set up, z goes on and on and on upwards, right? To stop that, we say, well, and also one more cut, like here, below this, right? And that is, where's that stupid thing? 12 minus 3x minus 2y. So, in summary, the bounds that we should have, if we're doing it as a triple integral, should be 0 to 12 minus 3x minus 2y. Then the y should range from 0 up to that equation we found for the intersection of the plane in the z equals 0 plane, namely 0 to 6 minus 3 halves x. And then finally, sorry, it's a little bit too crowded. I don't like that, but oh well. And 0 to 4. We should have variable bounds. This is the bounds that are written on the next page here. Horrible. Those are rectangular bounds. All right? So like the z bound is okay, actually. Unless I'm misreading the problem. I don't think so. Right. Yeah, there's a significant error here. So, I mean, the first step is okay. That is, after I do the integral of z, I've got, what I'm trying to say is this is okay, except that these two bounds are totally bogus. Totally bogus. All right? So we'd actually have to do this. All right? Incorrect. And it might be useful, though, to think about what would that actually be? What's that say? That says 0 less than or equal to x less than or equal to 1. That says minus 2 less than or equal to y less than or equal to 3, right? So what we're looking at here, this claims to be a volume that it's not. In fact, this volume, right, what it is the volume over the rectangle, 0 between x being between 0 and 1, y being between minus 2 and 3. So it's something like this rectangle is my r, all right? And so what it's doing is it's calculating the integral of 12 minus 3x minus 2y dx dy over that region r, which is lovely, but it's just not the volume that is something, but it's not the something we're looking for. And I'm not sure exactly what that volume looks like, or even whether or not the I'm not sure whether the plane this plane z equals 12 minus 3x minus 2y, is it actually above the xy plane over that rectangle R? What do you guys think? Is my picture legitimate? I mean, is this actually the volume, 95 over 2? Is that actually the volume of this shape? Admittedly, it's not. It's not what we're purportedly calculating, which was this thing, right? Yeah.
For it to be volume, wouldn't it have to be 3 integrals in the beginning instead of 2?
Well, again, we can calculate volume by calculating the integral of f over dA. That calculates the area between z equals 0 and z equals f of xy, limiting the domain of f to be the region R. My question again, though, this right here, 12 minus 3x minus 2y, is that positive? Or at least non-negative over that rectangle? How would you figure that out? Hey, we can use min-max stuff, right? What's the gradient of that function? Yeah, minus 3 minus 2. So there are no local mins or maxes for the function, right? So any extreme of the function must happen on the edge. So really, to figure out how that function behaves, the plane behaves, it suffices to think about it on the edge. So what happens when you put x equals to 0? In here, you get what? 12 minus 2y. What about 12 minus 2y between minus 2 and 3? What's minus 2 when you put it into 12 minus 2y? You get 14, right? 16, thank you. And then what happens when we put 3 in? We get 12 minus 6. So apparently y ranges between 6 and 16 in this graph. That's positive, hopeful. What about the x when we fix y equals to 0? What happens there? We've got x ranging between 0 and 1, right? Which means we're ranging between 12 and 9. Again, x is positive there. How about y equals to the other extreme? Oh, I shouldn't look at y equals 0. I should look at y equals minus 2, right? Y equals minus 2 gives me 16 minus 3x. Again, that ranges between 16 and 13. And if I plug in, so what I'm saying to say is just plug in the endpoints and see what happens. You can pretty quickly see that on the edges, the graph is positive. So we are actually calculating the volume 95 over 2. Did any of you guys ever study geometric, or what's called linear programming in like your high school algebra class? Did you ever do this thing where you're given an objective function, like f of xy equal to something like 3x plus 2y, and then you're given something like, you've got this set of inequalities, something like, you got some region bounded by inequalities, and you're supposed to figure out in that region bounded by like linear inequalities where the function, your objective function, is largest or smallest. No one studies this in high school algebra anymore. Really? How about college algebra here? Also not? I learned it in college algebra personally. I did not take college algebra at an elite academic institution, I will tell you. I mean, I took college algebra at community college. We learned it there, but I guess that was 1996, so whatever. This math no longer matters, apparently. But anyway, this actually does matter. It's the kind of thing you come up with. Often in a business, you have some objective, which is basically linear combinations of your variables. And if you have 2 of them, and you have things like budgets, which say that there's a certain minimum or maximum to the variable, you end up with some sort of region which is bounded by lines. If you use what we've done this semester, you can easily understand what geometric programming says, which is, well, the gradient of f is 3, 2, right? That says that all of the mins or maxes have to be on the edge. There is no local min or max. And then, when you think about a shape like this, if all the edges are linear, right? When you study the restriction of this function to any of these edges, it's again linear, which means that there's no local maximum in each edge. So what you're left with is a really simple rule. If you want to find the maximum or minimum of such a function on something with edges that are lines, all you got to do is check the values of the function at the corner points. This is what's called geometric linear programming. It says to solve to maximize an objective function that's linear in two variables, you just like graph the so-called feasibility region and check the corner points. That's all you gotta do. Sorry. I'm wasting your time. I know you haven't seen this before, and so I guess oh well. I need to talk to the people teaching college algebra here. That should be in our course. Alrighty. Did you miss that day at the Emporium? Was it?
I was asked, are we going to take attendance?
Attendance. Curses. Got me. It's pretty good. Let's see here. Where was I? 2, 3. You see, this is getting depressing for me. I get my hopes up. All right, somebody's got actually an actual question, and then no, it's just the fishing for attendance points. Mr. Zader, I'll find your card later. All right, so I had this. My spider sense was tingling that I should look at the notes today because I had a feeling that the person who edited my notes has not been as thorough as I would like, because I'm quite sure that when I taught this student Calculus 3, that we found that this was an error and it should have been removed. Hey, so as you find these, let me know about them. There are a few like this. If you can't understand the calculation in the notes as you're working through them, let me know. All right? There exists another possibility, which is that I have misread my example. I don't think so, though. See, look at this. Check this out. The next problem, I somehow have regained the ability to do mathematics. Find the volume of the tetrahedron enclosed by the coordinate planes and the plane 2x plus y plus z equal to 4. This is the same problem with a different plane. Notice now, I start out well, and this d, I do not put constant bounds on both, right? Because when you look at the picture, it's just like the one we just did. There's some triangle that we should be integrating over. And that triangle is given by 0 less than or equal to y less than or equal to 4 minus 2x, and x going between 0 and 2. As you can see, I have variable bounds, as I ought to. So, if you're going to study an example, if you have to pick one of them, pick example 17 is my point. Yeah.
I actually got an actual question this time. So for the last one we were doing, you have like x between 0 and 4.
Yes.
There was like a function given on your notes for that one before. Like when you were writing, how come that one doesn't have like a function as its bound for x?
What? So
There was like when you had each function right now for like the bounds.
oh, so that picture, this picture you're talking about, right? In this picture, you can see how to set up different, like we actually looked at how to set it up 6 different ways. So those are intending in that direction. The point is, this is the largest x ever gets, 4, 0, 0, so that's why x goes from 0 to 4. Let's see here. It might be instructive, though. In fact, since you're asking the question, it's definitely instructive to set up this integral a different way, right? So suppose we wanted to set it up. What if we wanted to set this integral up instead? Suppose we want to set up the volume as integral. I'm making my bounds, leaving myself some room. So suppose we wanted to do, instead of z first, we want to do y. And then the z dx. Oh, I want to put x next and then z last. All right. So let's look at, if I'm going to choose that ordering of bounds, how would I have to set that for this particular shape, this particular solid? how do I set up the bounds? All right. So what is z? Let's do the easiest thing. What's the maximum? What's the z ranges from? Well, first of all, let me do the easy thing, because I said that it's bounded by the coordinate planes. So that puts a 0 here, a 0 here, a 0 here. So that's for free, essentially. How big does z get? 12. So that means that the outside bound goes to 12. All right. So if we want to think about it in terms of sculpting, we are basically looking at this infinite horizontal slab from z equals 0 to z equals to 12, right? Then my next move, I guess, I want to do what? I try to think. I have to think. Oh, I want to write y. Solve for y. Curses, where's this stupid, where's the graph to start with? I mean, the equation of the plane was what? X plus 2y plus 3z equal to 12, was that it? Or what was it? Oh, 3x plus 2y plus z equal to 12? Okay, so let's see here. So the y, to solve for y, I get y is equal to 12 minus z minus 3x divided by 2, right? So looking forward, I know that I need this here. I've divorced myself from my sculpting idea for just a second. Sorry about that. Let me think about it. So that's y like this. I should be thinking about this as my next cut, basically, which is what? This line right here has, what is it? Z equals to 12 minus 3x. So for y equals to 0, we get z, what did I just say? 12 minus 3x. Z equals to 12 minus 3x. But I need to actually bound x, right? So this says x is what? Z minus 12 equals minus 3x. So x equals to 4. Good grief, I can't do algebra. I'm trying to solve for x. Z minus 12 divided by minus 3 equals to x. In other words, 0 less than or equal to x less than or equal to 4 minus z over 3. That would correspond to sort of taking that horizontal half, I mean, we have a slab. So the slab would be something like, right, like this. It goes on, and then like chop that. Let's see here. No, like this. So it gets chopped like that, and so it's still this red shape goes on and on and on. Still, if I put here 0 less than or equal to 4 minus z over 3, then the final cut, right, is this right here, which says like that. So my picture gets too horrible. I'm sorry. I just, you have to kind of imagine these things as opposed to really try to literally draw them. But that would be the setup if we went that way. You know, there's some things you can look for in your setup to tell whether you're right or wrong, right? As you're setting up the iteration, if you end up with a letter after the integration, which remains until the end, if your answer has like a naked x or y or z in it, you did something wrong. The answer here at the end of everything should be a number. Could be 0, could be positive, could be negative. but we're looking for a number here. So if your setup somehow leaves you variables after everything's done, you did it wrong. I think we should be okay here, right? The y integrates to give me this, then the x integrates, and after this integral is done, we're just left with a function of z, and then z integrates from 0 to 12. So, all right, I'm tired of talking about these. I'm going to change gears here and go on to the next topic, if it's okay with you guys. Is that right? All right. Whew, goodness. So I'm scared to look at the other examples in the notes. I'm afraid what we might find. All right. So the next topic is coordinate change. For multivariate integrals. So in other words, what I'm going to try to communicate to you guys next is you might have asked, I mean, a natural question you might have asked at this point, in Calculus 1, what do? We talk about, okay, here's your notion of antiderivative, and we'll teach you the fundamental theorem of calculus, right? And we start doing stuff like finding areas bounded by graphs and so forth, and so forth. And then at the very end of the course, we introduce you to what? We introduce you to something called U substitution, right? How to take an integral that you have in terms of x and change it to a new variable u. How's that go? And what did we learn for U substitution? Yeah, you have to change the bounds. What did we not, excuse me, let me restate that. What did no one actually learn for U substitution? You should change, sorry, I'm being pessimistic here, but so often students do not change the bounds. The kicking and screaming, being dragged through various forms of medieval torture, they will change the bounds, or if you pay them enough, I guess, I don't know, but yeah, it's hard to get students to change bounds, my experience, which is, I have considerable experience in this matter, and it's not encouraging, but anyway, so yes, change the bounds, and of course change the integrand, right? And last but not least, change the measure, or you have to trade your dx for du, right? There's those three things going on. Reformulating the integrand, reformulating the bounds, and reformulating the measure, or the differential, if you will. All three of those things have to work in concert to make a U substitution successful. So the question that we're asking now is, what's the analog of that for multivariate integration, all right? So here's the theorem. The theorem says that if we integrate, I'll start with a double integral, f of xy dx dy over some region R, then that's actually equal to the integral over S of f of x of u comma v, y of u comma v, times the absolute value of the Jacobian of xy with respect to uv, du dv, where S is the transformation of R into the UV variables, UV plane. And furthermore, this right here is, by definition, so ignoring, these guys here are absolute value bars. All right, but the definition of the Jacobian is just, it's a determinant. This is the determinant of what I would call the Jacobian matrix. The Jacobian matrix is xu, yu, xv, yv. So specifically, that is what? X u y v minus x v y u. This is the change of variables theorem for two variables. There's a three-variable version of this. For three variables, I'll say b, you got your f of x, y, z, dx, dy, dz, and you have to transform your b, let's say to, I don't know, I'll call it b tilde, there we go. And you got your f of x of u v w, y of u v w, z of, you guessed it, u v w, and then you have to multiply by the absolute value of the Jacobian of x, y, z with respect to u v w, du, dv, dw, where again, the Jacobian of x, y, z with respect to u v w is actually meaning the determinant of what I would call the Jacobian matrix is the determinant of xu, yu, zu, xv, yv, zv, xw, yw, zw. These are partial derivatives. Now I can explain why these theorems are reasonable, but it takes me about 20 minutes or so and some pictures, and I'll get back to that most likely tomorrow. But I just wanted to state the theorem plainly for you so you can see what we're after, okay? And work an example, then I'll motivate why these theorems are true in due time. Yep.
Why did you use B in like a B squiggle line? Is that just...
It's not B anymore, it's the transformed.
Okay, so you just you could have used A.
Yes, you could have used A, you could use Pac-Man, whatever you like. Here, let me just do a couple before I get lost in the theory and so forth. All right. This is, so tomorrow hopefully I'll explain how this ties into, I told you guys about the general notion of a derivative in here. And you might have noticed we didn't really use that anywhere. One of the places where that gets used is in understanding this theorem from a more big picture perspective. So I'll do that tomorrow. Example, how about this? We want to integrate over x squared plus y squared less than or equal to, I don't know, 4. And how about the square root of x squared plus y squared times, I don't know, let's say inverse tangent. Oh no, let me not make this complicated. Let's just say, that's good. X squared x plus y squared dx dy. All right. Let's do this one. It's actually geometrically kind of interesting what this is. Like this is the volume. So it's fun to think about what this is just for a second. So this, the square root of what happens to this square root of x squared plus y squared if you look at the, if I put x equal to 0, what happens? If I put y equal to 0, what happens? It's the square root of x squared or it's the square root of y squared. What is the square root of x squared? 2? 2. Square root of x squared is not 2. No. Plus or minus x? Yes. In this context, I think it would just be... Oh, but I said square root, so it's plus, right? So, I mean, the square root of x squared is the absolute value of x. In fact, that's a definition for absolute value of x, if you like. So the point is that this, if you look at the coordinate planes, you can see it's just like the line y. It's just the line with slope 1, and then it's, I don't know. So this is basically some sort of like one of these deals. Like It's a drilled out cylinder. It's the volume of something like that.
So
Yeah.
it's like the volume of the space outside of the cylinder instead of the volume of the cylinder itself. I mean, not of the cylinder, but like a.
Well,
of the cylinder or
if this was like a, you know, if we're looking at a, let's see here, if we're looking at a piece of a metal disc that was 2 units thick, and then we drilled this sort of conical bit out of it, it would be the volume of metal left after we drilled the top with that little indentation. Okay, anyway, I digress. Let's get back to the theorem. Actually, it doesn't matter what it looks like. The point is, this screams at you. It should scream at you polar coordinates. So we make x equals to r cosine theta. We make y equals to r sine theta. See, this is my quote-unquote r, my initial region. What does that look like in terms of polar coordinates? Right, so in terms of polar coordinates, if I look at the polar plane, if I look at, you know, r this way, and I don't know which one, does r go this way and theta go that way? Which was, I don't know. Whatever, however you want to do it. If I make r go that way, and if I make theta go that way, we go 0. Basically, it's a rectangle, right? Because we have 0 less than or equal to theta less than or equal to 2 pi, and we have 0 less than or equal to r less than or equal to 2. I mean, this is the S I'm talking about over there, the transformed region in the new coordinates. Right? So I integrate 0 to 2 pi, integrate from 0 to r, excuse me, 0 to 2. This is, what's the square root of x squared plus y squared? This is literally r. Now I have to change the dx dy. The theorem tells me how to do that. See, what this theorem really says, if you want to think about it heuristically, what the theorem says heuristically is that dx dy is equal to the Jacobian, the absolute value of that, du dv. That's essentially what the theorem says if you want to sort of distill it to a heuristic. So what is that here? So we should be looking at the determinant of xr, yr, x theta, y theta in this context. My r is u, my theta is v, quote unquote. All right? But what is that? What is the partial derivative of x with respect to r? Cosine theta. And y with respect to r? Sine theta. And how about, what is the x derivative with respect to theta? It's minus r sine theta. How about the y derivative with respect to theta? R cosine theta. What happens when we take this determinant? We get r cosine squared theta plus r sine squared theta, also known as r. All right? So in this particular case, the absolute value does nothing because r is already positive. So absolute value of r is still just r. Or for some of you, r. I'm sorry, that was horrible. But it's been said. So this is r from the Jacobian. And then, again, the usual rules of setting up bounds still apply. 0 to 2 is my dr, 0 to 2 pi is my theta. And so what do we got? And then we just integrate. So we got the, we got integral from 0 to 2 pi. That gives us 8/3, right? So I calculate 16 pi over 3. because the d theta integrates to give me 2 pi. And the r squared over, well, the r squared integrates to r cubed over 3, right? But 2 cubed is 8, so that gives me 8/3. Yeah. By the way, there's a takeaway fact. dA is r dr d theta in polars. What's dA in Cartesians? Right. So this is the so-called infinitesimal area element. Here's another one we could do. If you wanted to integrate over x squared plus y squared plus z squared less than or equal to 4 for z positive, all right, of, let's say, x. Let's say z, dx, dy, dz. All right? How would you do this one? So what is this region? It's the upper hemisphere, right? I made it have basically 0 less than or equal to rho less than or equal to 2, where rho is the spherical radius, remember? Rho is the square root of x squared plus y squared plus z squared. So in terms of spherical coordinates, the bounds here are really nice. I just go 0 less than rho less than 2. How about theta? What is theta? So theta goes all the way around, right? So we get full sweep for theta. How about phi, though? What about the colatitude, as we call it? So this is, you know, this is phi, right? 0 up at the North Pole, less than phi, less than or equal to what? Not pi. Pi would go the full, that would give you the full sphere. Pi over 2, because pi over 2 is where you want to be. Because remember, we have the formula, z is equal to rho cosine phi, right? Z is equal to rho cosine phi. So if this is z equals to 0, right, that's where phi is equal to pi over 2. So if I change the bounds to spherical coordinates, I go 0 to 2 for my rho, 0 to 2 pi for my theta, 0 to pi over 2 for my phi. Then I have to change the z into spherical coordinates. That's easy enough. That's rho cosine phi. See, this z is rho cosine phi. But then we have to face the music. See, because dv, the infinitesimal volume, in Cartesians, dx, dy, dz, but that in spherical coordinates would be partial x, y, z, partial rho, phi, theta, d rho, d phi, d theta. That's a 3x3 determinant, which I will work out in gory detail probably tomorrow. I will just tell you, for the moment, I believe, this works out to rho squared sine phi d rho d phi d theta. And so when we change the measure, this puts a rho squared sine phi. And I got to be careful here. This should be d phi d theta d rho because of the order of the bounds. This is wonderful news because this means we don't have to suffer through integrating square roots in Cartesians, right? We can convert to an appropriate cylindrical or spherical bounds and get around the horror, which would be integrating square roots. You're like, but I like integrating square roots. I missed trig substitution from calculus too. Let's go back to that. I didn't really learn it the first time through. I'd like a chance to reevaluate my understanding of trig substitution. No? No? Yeah. It's pretty much the only way I can have a conversation with people about trig substitution is to teach calculus 2. Kind of sad. If you go to your pastor, start talking about trig substitution. I mean, he's a nice man and all, but how long is that conversation going to last? Not that long. Not that long. So if I could somehow control the grade of my pastor, or just generally people in life, right? You know, it's a thing. All right, I shut up. See you guys tomorrow.